Look around, and the world can feel entirely unpredictable. A soccer ball curving in midair, a pot erupting into the erratic bubbling of boiling water, or massive planetary bodies tracing distant ellipses in the dark. For centuries, humans viewed these as isolated, almost magical events. Physics approaches them with a completely different logic, the idea that these highly varied events are all driven by the exact same underlying mechanics. At its core, physics is the study of matter, motion, and energy. The ultimate objective is not to catalog a massive encyclopedia of isolated facts, but to formulate a small set of comprehensive principles that govern the entire observable universe. To find those rules, we have to look through a framework we can call the scales of reality. The physical laws dictating how an object behaves change depending on how big that object is and how fast it's moving. To understand how reality is built, we have to abandon our everyday human perspective. We must zoom way out to the extragalactic scale and dive all the way down into the subatomic to see exactly how these universal laws evolve. We start in the middle, at the human scale. This is the realm of classical mechanics. It deals with macroscopic objects moving at relatively slow speeds. If you drop an apple or roll a pair of billiard balls into each other, the resulting motion follows a highly predictable path. This predictability extends to energy transfer, governed by thermodynamics. What we feel as heat is the random, chaotic motion of a material's molecular constituents. Placed in an isolated system, those bouncing molecules distribute that energy until everything reaches a uniform temperature, a state known as thermal equilibrium. This chart shows the complete spectrum of electromagnetic radiation. It reveals that the visible light we use to see the world is just one tiny sliver of a massive spectrum of waves, stretching all the way from long radio waves to highly energetic gamma rays. Because these classical laws are so precise, scientists by the end of the 19th century drew a logical conclusion. The universe operated like a perfect clockwork machine. If you knew the starting state of an object and the forces acting upon it, you could calculate its future with total certainty. Those classical rules perfectly engineer our everyday environment. But the moment we push past our immediate surroundings into the extreme limits of the universe, that perfect machine completely breaks down. When we zoom out to the extragalactic scale to look at incredibly massive objects, or objects traveling close to the speed of light, Isaac Newton's predictable mechanics fail to match observation. To explain this, Albert Einstein proposed general relativity, which requires us to rethink the empty space between objects. This illustration shows the four-dimensional space-time continuum. Instead of a fixed, empty stage where events unfold, space and time form a single, flexible fabric. This theory redefines gravity. Instead of an invisible rope pulling two objects together, gravity is the physical curving of that space-time fabric by a massive body. It creates a geometric dip that dictates the orbital path of any smaller object passing by. Einstein's special relativity goes further, establishing the speed of light as a constant limit for all observers. This causes bizarre effects, like time slowing down and physical lengths contracting as objects approach that speed limit. At this cosmic scale, we view gravity and motion as direct physical responses to the very shape of the universe. Now we zoom down into the microscopic scale of the atom. Down here, both classical mechanics and relativity fail to predict what happens next. Atoms are not solid, indivisible objects. This diagram illustrates the subatomic constituents known as hadrons. We can see that familiar protons and neutrons are composed of even smaller elements called quarks, which carry bizarre fractional electrical charges. The behavior of these tiny constituents is described by quantum mechanics. This visual compares two models of atomic structure. Energy at this level doesn't flow continuously. It moves in discrete, restricted jumps, and the particles themselves exhibit wave-like behavior rather than acting like physical solids. This leads to the uncertainty principle. At this scale, it is physically impossible to precisely measure a particle's exact position and its exact momentum at the same time. At the most foundational level of matter, the strict determinism of the human scale vanishes. The universe is not a predictable clockwork machine, but rather an unpredictable, mathematically defined web of probability. Returning to our human perspective, we are left with a massive scientific paradox. We have highly accurate laws for the very massive in relativity, and highly accurate laws for the very tiny in quantum mechanics. But if you try to apply them simultaneously, they contradict each other. Physical laws are never complete. They are always subject to modification. To figure out where the math meets, scientists conduct massive experiments, smashing particles together at high energies in huge accelerators, looking for new data that might bridge the gap. This is the ultimate objective of modern physics, to formulate a single, unified theory of physical phenomena that seamlessly connects matter, motion, and energy across every possible scale. A complete theory of everything has not yet been achieved. Yet, the remarkably small set of rules we do have successfully accounts for nearly every known phenomenon we can currently observe. Physics identifies the mathematical principles that drive every interaction we observe, proving that beneath the visible chaos of nature lies a profound and beautiful order.